Welcome to LectureCast, where we discuss general chemistry topics. This is a podcast lecture series on general chemistry. Today, we will be talking about chemical equilibria. My name is Mr. Ferguson. I am a adjunct faculty, and I'm also an associate member of the Royal Society of Biology and associate member of the Royal Society of Chemistry. Hello and good evening, everyone. What a moment where everyone is on their feet, holding a flag and supporting their concept. Team Equilibria on one side of the field and Connects on the other side of the field. Now, let's get ready to rock and roll. These two experimenting concepts exemplify in the spirit of chemistry that skill displayed in different ways, perhaps, but by world-class chemists again. There is history to be made or added, concepts to be learned, and skills to be gained. Just before we dive into the concepts, I want to remind everyone you are not alone. This is an academic community. Remember to get help when needed. Reach out to university services if needed. Never give up. Keep trying. We are here to help you be intelligent, ethical, and responsible scientists. But at the end of the day, you must be responsible, ethical, and hardworking. So let's talk about Le Chatelier's principle. When a system at equilibrium is disturbed by a change in the amount of a reactant or product, a change in volume, or a change in temperature, the system shifts in a direction that minimizes the disturbance. So a quick overview, we'll discuss the equilibrium constant. Remember the word extent. We'll talk about dynamic equilibria. Remember a treadmill. The equilibrium constant expression. Remember the law of mass action. The equilibrium constant. States of matter and the equilibrium constant. Calculating K. The reactant quotient. K and pressure, find equilibrium concentrations, and the Chatelier's principle. These are just a few of the topics we will cover. In some of these topics we will cover today. The rest we may cover in later episodes. So the equilibrium constant. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. Let me say that again. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. One more time. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. The equilibrium constant. The equilibrium constant measures extent. How far a reaction proceeds towards products. How far a reaction proceeds towards a specific point. So a large K, much greater than 1, indicates a high concentration of products at equilibrium. A large K, much greater than 1, indicates a high concentration of products at equilibrium. The equilibrium constant measures extent. How far a reaction proceeds towards products. A small K less than 1 indicates a low concentration of products at equilibrium. Dynamic equilibrium. Most chemical reactions are reversible. They can proceed either with the forward or the reverse reaction. Depending on the type of reaction you're referring to, certain steps may be more or heavily weighted. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. One more time. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. So dynamic equilibrium. However, this does not imply that the concentrations of the reactants and the products are equal. So, the reaction being at equilibrium does not imply that their concentrations of the respective reactants and products in that reaction are equal. Now let's talk about the equilibrium constant expression. The equilibrium constant expression is given by the law of mass action and is equal to the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. So when you look at the reaction, you see that there are numbers in front of those chemical symbols, those are typically referred to as the stoichiometric coefficients. So when you write an equilibrium constant expression, you put the concentration of the reactant in brackets, in square brackets, and the exponent for that square bracket term is the stoichiometric coefficient, and it's products over reactants. So also, the equilibrium constant can be expressed in terms of concentrations or in terms of partial pressures. Remember the relationship between pressure and concentration within the context of moles? The two constants are related. Concentration must always be expressed in units of molarity for Kc. Partial pressures must always be expressed in units of atmospheres for Kp. The equilibrium states of matter and the equilibrium constant. The equilibrium constant expression contains only partial pressures or concentrations of reactants and products that exist as gases or solutes dissolved in solution. Pure liquids and solids are not included in the expression for the equilibrium constant. One more time, the equilibrium constant expression contains only partial pressures or concentrations of reactants and products that exist as gases or solutes dissolved in solution. Pure liquids and solids are not included in the expression for the equilibrium constant. So calculating K. We can calculate the equilibrium constant from equilibrium concentrations or partial pressures by substituting measured values into the expression for the equilibrium constant as obtained from the law of mass action. So what does this mean? We can calculate K given the concentrations or partial pressures when we have those measured values. As we progress in this discussion, we'll also in later episodes we'll introduce the idea of using ice tables in which you look at the initial change and equilibria concentrations. You look at what you start off with, the change, which can be denoted by some x, some variable term, and then you net, or the net expression would be the initial minus the change, and you use those terms at the bottom. The E section of the table, use those terms. You form an expression using the law of mass action, and from that expression you equate it to the known equilibrium constant, and you solve for x, and you're able to obtain the different concentrations of the reagents at different points in the reaction in order for you to progress and solve the problem. So calculating K. In most cases, we can calculate the equilibrium concentrations of the reactants and products, and therefore the value of the equilibrium constant from the initial concentrations of the reactants and products and the equilibrium concentration of just one reactant or product. So one more time, in most cases, we can calculate the equilibrium concentrations of the reactants and products, and therefore the value of the equilibrium constant from the initial concentrations of the reactants and products and the equilibrium concentration of just one reactant or product. Now, depending on whether the type of substance or reaction that you're referring to, that may be easier said or easier done. So you really have to know the reaction, understand the reaction that you're referring to. For example, with strong acids and strong bases, it's very easy or relatively easy when compared to weak acids and weak bases. So if say you have the equation is A plus B turns to C plus D, where the stoichiometric coefficient of A is little a, the stoichiometric coefficient of B is little b, the stoichiometric coefficient of C is little c, the stoichiometric coefficient of D is little d. That will be, if you're looking at the video that will be posted eventually, it will be capital C in brackets raised to lower c, capital D in brackets raised to little d over capital A in brackets raised to little a, and capital B in brackets raised to little b. And this is derived from the concept or the expression in which you denote terms that state or show that the forward rate is equal to the reverse rate. So the reaction quotient. The reaction quotient, Q, is the ratio of the concentration or partial pressures of the products raised to their stoichiometric coefficients to the concentration of the reactants raised to the stoichiometric coefficients. And the key thing to remember, the difference between Q and K is Q is at any point in the reaction. K is at equilibrium. So, It's important to know the reaction coefficient, the reaction quotient is at any point in the reaction. The equilibrium constant is at K. At K. The reaction quotient is the ratio of the concentration or partial pressures of the products raised to the stoichiometric coefficients to the concentrations of the reactants raised to the stoichiometric coefficients at any point in the reaction. The reaction quotient, like K, Q can be expressed in terms of concentrations or partial pressures. At equilibrium, Q is equal to K. Therefore, the direction in which a reaction proceeds can be determined by comparing Q to K. One more time. At equilibrium, Q is equal to K. Therefore, the direction in which a reaction proceeds can be determined by comparing Q to K. If Q is less than K, the reaction moves in the direction of the products. If Q is greater than K, the reaction moves in the reverse direction. If Q is less than K, the reaction moves in the direction of the products. If Q is greater than K, the reaction moves in the reverse direction. So finding equilibrium concentrations. There are two general types of problems in which K is given and one or more equilibrium concentrations can be found. For the first type, you have the equilibrium constant given and all but one equilibrium concentrations are given. We solve this type by rearranging the law of mass action and substituting the given values. For the second type, K and only initial concentrations are given. We solve the second type by creating an ice table and using a variable x to represent the change in concentration. And depending on our equilibrium constant, whether it is smaller than 10 to the minus 5, we can use the x as small approximation. When you do the x as small approximation, whatever you subtract x from, the ratio of those things when multiplied by 100 should be less than 5%. If that's not the case, the approximation won't be as sound. There are two general types of problems, again, in which K is given and one or more equilibrium concentrations can be found. First type, K and all but one equilibrium concentrations are given. We solve this type by rearranging the law of mass action and substituting the given values. Second type, K and only initial concentrations are given. We solve the second type by creating an ice table and using a variable x to represent the change in concentration. Equilibrium is so important. When a system at equilibrium is disturbed by a change in the amount or reactant of a reactant or product, a change in volume or change in temperature, the system shifts in a direction that minimizes the disturbance. So ladies and gentlemen, it was an exciting match. At the end, the scoreless first half and 3 huge goals in the second, including the Chatelier's winner at the wire. The classical goes Equilibrium's way on enemy ground, and all the reactions continue until we meet again for the Classico Acidica and Basissio. Hope you're doing well. Hope all is well. Continue to read, continue to study, continue to prepare. This is just a preview of more to come in terms of equilibria, acids and bases, dynamic equilibria, and other concepts associated with thermodynamics. And you're dropping it like it's hot. You can think of primary protein structure, what it is and what it's not. Yo, most of this rap can be placed in a jar because we're mainly looking at the groups of the R. Polar side chains, same GATC. You stick with me just like glue. Glutamine. Asking all the questions. The one letter abbreviation is Q from the peptide backbone with a methylene. Then a methylene attaches a carbonyl. Ooh, relax, please be still. Then there's the amine. Asparagine. Listen closely to me, my friend. The one that abbreviation is N with a CH2. Then a carbonyl. Attached, still on the screen, is the amine. Yo, check out tyrosine in your magazine. The one that abbrev is Y. Yeah, that's a catch. Look at what's attached. A methylene, then a phenyl, and to that a hydroxyl. Amino acids, polar side chains.
See, senor. Do you get what I say? Forget that, let's focus on cysteine today with the methylene. And attached is a sulfur hydro. Don't lose focus for you be idle. Yeah, the one I breathe is C. Are you following me? Now let's look at the one for T called threonine. Now you see with the CH attached is a methyl, and to that same CH is a hydroxyl. Yeah, the group attached almost looks similar to an alkoxyl. Talk about a line. Yeah, this is rap and biochem combined. Focus, now we're looking at serine. Attached is a methylene and then a hydroxyl. The one letter brief is S. Well, I must confess, I'm interested in being a pro, not to be vain, bro, cause we're looking at non-polar side chains. Non-polar side chains. Garvel, protrip, methyphen, glycine, alanine, valine, isoleucine, leucine, and proline, tryptophan, methionine, phenylalanine. Can you comprehend? Yo, proline, pro, for even shorter say P, the backbone of this time, you see. There is instead, ooh, an NH2 positive, and to that NH2 is a methylene, then a methylene. And just before we close the ring at the peptide backbone is a methylene. Yeah, in alpha helices, this could cause kinks. We talking about the chemical kitchen zinc. Yo, I went to Neverland with Peter Pan. Yo, let's look at tryptophan with a one letter brief W. With pixie dust I flew. I went to tech reptable. Attached is a heroic system with pyrrolium and a benzene ring smacked by it. Forget it. Forget what? Spill of fried fish for Friday. The judge was from the Fresh Prince, who was from Philly. Yeah, we're looking at phenylalanine. The one that I breathe is F. Okay. Do you remember Jeffrey? Yo, what's the group that's attached? Just a benzyl group. Yeah, just that. Yo, Dr. Rhyme, hurry up so we can finish in time. Met, guess who I just saw? Stop, let's call it a draw. Methionine with a one letter brief of M. With a methylene, then a methylene. Yo, me done for. And a sulfur. And at the end, a methyl. Yeah, we bustin' rhymes like Hansel and Gretel. Bro, take a break. Look at the TV screen. Look at it. It's glycine with the one letter brief, simply G. Attached is a hydrogen. Oh really? Shower. Open sesame, cause I'm Allah. Alanine. We simply say a methyl is attached. Pristine. Okay, it has a one letter brief of A. Wonderful. Excellent. Very good guys and vowels. Valine is very worthwhile with a CH attached. And to that same CH2 methyls are attached. With the bond and stick method, it looks like a V is attached simply. Yo, Lewis electron dot structures. We draw a lot. Leucine, yeah. Sing along. The chain has a unique design like my song. With a methylene, then a CH is attached, and attach is two methyls. Yo, similar in bond line to its bromine line, except when we draw the methylene before the V, it's getting very easier, you see. Yeah, let's isolate isoleucine with a CH attached to it. One side is a methyl, and to that same CH on the other side is a methylene, then a methyl. Wow, we cleared Ebola, and look, we're finished with the non-polar amino acid side chains. Now let's look at some that are very strange. The electrically charged amino acid. Stall, drum, roll. Yo, don't like to be late. Yeah, aspartate. It is very great. With the one letter brief of D. It's an electrically charged amino acid, you see, with a CH2 attached, and also is a carboxylate. Yeah, that's very great. Come on, let's look at glutamate with the one letter brief of E. Excellent, gregarious. Let's see. Now let's look at what's attached. A methylene, then a methylene, and also a carboxylate. Glutamate and aspartate make an acidic slate. Yo, histidine sounds like histamine. The thing that is up when I have a cold. Attached is a methylene and an imidazolium. The one letter brief is an H. Yeah. Okay. Let's look at one with a one letter brief of K. Lysine. Hooray. Yo, when I get cheap rings, they have cubic zirconium, but when I get the lysine chains attached is a butyl ammonium. So let's look at arginine. R with a one letter brief of R. Bizarre. Yeah, a good name for a rhino with a group attached like a propyl guanidino. With a group attached like a propyl guanidino. Yo, you know what I mean. Acidic chains are glutamate and aspartate. Basic chains, histidine, arginine, lysine. Yo, we cannot forget polar amino acids. Zinc, GATC, serine, threonine, glutamine, asparagine, threonine, cysteine. And your non-polar boys, Garville, Protrip, Methyphen. Come on, let's make some noise. These are our favorite toys. Glycine, aline, valine, isoleucine, leucine, proline, tryptophan, methionine, phenylalanine. Can you comprehend? Amino acid rap. Amino acid rap. Amino acid rap. Shout out to my friends, future docs, what you say. But all we want to do in class is simply get A's. People always wonder why I'm so good with rhymes. I'm from the Bahamas where each moment is sublime. When poetic and cultural excellence is the order of the day, cool rhymes become easy to say. Yo, I think as a rapper I need to quit because I'm not really that legit. But as a biochem student, I can learn all the time, and when I study really hard, I can be Dr. Rhyme.